We're not going to have time to really talk about cosets today, but they are super important, I emphasize once again. Again, keep working on these properties, keep working on getting these properties into your heart and soul. Just remember them just like that. Okay? Maybe spend some time thinking about them every day. Not just memorizing them, but thinking about why they make sense. Do quick little proofs in your mind if you can. I think for the sake of time in talking about the Orbit-Stabilizer Theorem's proof, I am just going to have to give an outline. And it says, let G be a finite group of permutations on a set S. And then for any I from S, I is an element of S. S is not necessarily a group. The order of G, the number of elements in G, is the product of these two orders. The stabilizer is a subgroup of G. It's the set of everything, every permutation in G that fixes I. And this is therefore the order of that subgroup. The orbit of I in G is not, it's a subset of S. And it's not necessarily a group. Because S is not necessarily a group. But I can still talk about how many elements are in that orbit. And if G is a finite group, that will be a finite set. And this product will equal the order of G. Again, that product is equivalent to the statement that the number of elements in the orbit of I under G is the ratio, the order of G divided by the order of the stabilizer. And that we know because the proof of Lagrange's theorem is the same as the index of the stabilizer of I in G. The number of left cosets, the number of distinct left cosets, that's the definition of index. It's something worth remembering. I could put that in the next quiz, for example. What's the definition of the index? I'll give you 4 choices. Distinct number of left cosets of this subgroup of that. It's also the same as the number of distinct right cosets. We mostly work with left cosets, it seems, but technically speaking, we could certainly think about right cosets. Mostly think about where A is on the left and H is on the right. That's a left coset. If you considered then the collection of left cosets of the stabilizer in G, consider that set, every element of the set is a left coset. Kind of a strange concept. This concept is going to be super important in chapter 9. Talk about factor groups. I mentioned that the other day. They're also called quotient groups, but our text calls them factor groups. The collection of distinct left cosets, I can prove this equality right there. I can find a one-to-one and onto mapping. Call it T. One-to-one and onto from that collection to the orbit. This is not an isomorphism we're talking about. Just one-to-one and onto, which would mean this equality would be true. The index, the number of left cosets, which goes with this set, would be equal to, well, okay, it would verify that these two things are the same. But we know this one is equal to that one by Lagrange's theorem. And therefore, these two things are equal. And therefore, these two things are equal. Got that? Say it again. If we verify T is one-to-one and onto, if we can find such a T, that verifies that these two things are the same. This goes with that, and this goes with this. We know from Lagrange's theorem that these two things are equal. Therefore, these two things are equal, and therefore these two things are equal. So what's T? T is to take an arbitrary left coset of the stabilizer in G and map it to something in the orbit of I. There's your arbitrary left coset. Alpha is an arbitrary element of G. The stabilizer is a subgroup of G. How can I map it to something in the orbit of I? Well, based on the symbols that I have, the only possible thing I could try would be alpha of I, and that fortunately does work. It's a natural thing to try. That is an element of the orbit. Of I under elements of G. But again, there's this fundamental issue. You can't just quickly show this as one-to-one and onto and be done. You also have to show it's well-defined, and this is an important thing. It's going to come up again. What if you had a different representative for the coset? Understand what I mean when I say that? What if you had beta as well that represents the same coset? Right? Cosets partition the group. They have different elements in them. In general, more than one element. Any one of those elements could represent the coset. Could be put in front of the coset to represent it when you write it symbolically. If this is true, if this is the same element of this collection of left cosets, then alpha of I better equal beta of I. It does, but that takes proof. Let me just say first of all that this is equivalent, like it came up on the quiz, to the statement that alpha inverse beta is an element of the stabilizer. That was one of the quiz questions, except with A's, B's, and H's instead of alphas, betas, and the stabilizer. One of the properties of cosets. But what does that mean? What does it mean to be in the stabilizer? It means when you apply it to I, you get I back. It stabilizes I. It doesn't move it. But this is equivalent to, if you say write it this way first, and then apply alpha on the left on both sides to that. So this assumption leads to this fact: this mapping T is well defined. Two different representatives of the same coset, alpha and beta, do lead to the same output for the function capital T. I purposely made it if and only ifs here, because the opposite direction has significance here too. If you assume alpha of I equals beta of I, in other words, T of beta stabilizer equals T of alpha stabilizer by the formula for T, that assumption leads to the conclusion that these two things are equal. The logic goes backwards. Which means what about capital T? If I assume this and can conclude that, what does that mean about capital T? Capital T of this equals capital T of that leads to the conclusion that the inputs are the same. Capital T must be 1-to-1, yeah. Which is part of what I wanted to show. After you show it's well defined. Is it onto? Give me an arbitrary element of the orbit. Call it J. Is there a coset that maps onto J? Well, that's based on the definition of what the orbit is. The orbit is the sum of all possible outputs, images of I, under different elements of G. For J to be in the orbit means there exists an alpha in G such that alpha of I equals J. And that alpha would be the alpha you put here to give you J. Got that? Given an arbitrary element of the orbit, I'm trying to show T is onto. To be in the orbit means there exists a permutation in capital G where this is true. That alpha would be what you put here to give you J in the end, to verify this mapping is onto. Let me erase the J since it wasn't there to begin with, but that verifies T is onto. That verifies these sets have the same size. And based on the assumptions here, the same finite size. Therefore, these two things are equal. We knew these were equal by Lagrange's theorem. Therefore, these two things are equal, and therefore these two things are equal. Okay? We'll look at some applications of the Orbit-Stabilizer Theorem next time. All right, for the rest of the day today, which is not very much time, we're going to talk about external direct products as much as we can get in 20 minutes here. Chapter 8. I think I may have forgotten to tell you to read it. And it would have been good if you read it by now. But I may have forgotten to put that on Moodle. You got a finite number of groups, G1 through Gn. Their external product, direct product, is, as a set, the set of all n-tuples. What's an n-tuple? Well, a 2-tuple is an ordered pair. A 3-tuple is an ordered triple. A 4-tuple is an ordered quadruple. A 5-tuple is an ordered quintuple, etc. An ordered n-tuple is a thing, parentheses, and n things with commas between them. It's just purely symbols. Collection of all such n-tuples with the ith component, you could say coordinate as well, but we'll stick with component, being an element of G sub I. I could be, for example, 4. The fourth component of this 5-tuple is D. Right? The fourth component of this 5-tuple is D. And where it's not just a set, it's a group, the operation is component-wise. Meaning, say A and B are in G1 and C and D are in G2, and I'm considering the external direct product of G1 and G2, so I want to multiply those 2 tuples, those ordered pairs. You do it component-wise. A gets multiplied by B in G1, and C gets multiplied by D in G2. Careful, this is not something you ever did in linear algebra, right? If these were vectors, you wouldn't do this with vectors, right? Unless you were adding them, which we will look at examples where we're adding. Though this has similarities with vectors in linear algebra, we kind of want to forget about that now, actually. A lot of times we do talk about linear algebra here, but kind of try to avoid thinking about linear algebra in vectors. Just take what you see here in chapter 8 as is. Our book denotes the external direct product in this way, which is a little funny to me. It was not the way I was used to writing it when I learned this subject. External direct product, and we have a bunch of pluses there with circles around them. Kind of weird. Here's the way I used to see it in books that I used. In other texts, the external direct product is, well, sometimes just called a direct product, and it's denoted by something like this, with time symbols rather than additions, multiplication symbols. But our text uses this, so we'll stick with this. And we'll still use the word product, even though you see pluses there. Do take the time to put the circles around the pluses. We're trying to emphasize this is something different from ordinary addition, or even ordinary multiplication. This notation is also a little bit more consistent with the idea of a Cartesian product of sets. which I do believe I talked about that maybe the first few days of class. I think I mentioned the Cartesian product idea. When you write down two arbitrary sets, A and B, and you write something like that, that's called the Cartesian product of A and B. A and B do not have to be groups. It's just the set of all ordered pairs. So as a set, this external direct product thing is a Cartesian product. And with Cartesian products, I've never seen people not use the times symbol. That always gets used with Cartesian products. A and B are not necessarily groups, just sets. But here we're going to use this notation. As a set, it means the same thing. How about some examples? Let's quickly make a Cayley table for Z2 external direct product with itself. So the set of all, as a set, it's the set of all ordered pairs whose elements are from Z2, whose components, first and second components, are from Z2. Z2 only has two things in it, right? 0 and 1. 2 times 2 is 4. This should have 4 elements. So as a set, it consists of these 4 elements. And if we want to make a Cayley table for it, we need 4 main rows and columns here. Black marker is fading, and let's try another one. Operation is done component-wise. 1, 0 plus 0, 1, for example. I'm using an addition here because the operation in Z2 is addition, is the same as 1 plus 0, comma 0 plus 1 is 1, 1. 1 plus 0 plus 0 plus 1. 1 comma 0 plus 0 comma 1, the sum of this thing with this thing is 1, 1. And it's going to be abelian here. Is it abelian? You could ask these kinds of questions up here. Is it abelian? Is it cyclic? Is it isomorphic to Z4? It's got 4 elements. Though we have seen groups with 4 elements that are not isomorphic to Z4, that are not cyclic to 4. 0, 1 plus 1, 0 is also 1, 1. Okay, this can be quickly filled in. 0, 0 is the identity. The group is abelian. 1, 1 plus itself. What's 1 comma 0? Excuse me, 1 comma 0 plus itself? 0, 0. 1 plus 1, which is 0 mod 2, comma 0. I'm doing addition mod 2 in both components. What's 0, 1 plus itself? Also 0, 0, the identity. What's 1, 1 plus itself? Also 0, 0, the identity. This group's not cyclic. Every element is its own additive inverse. It's not cyclic. It's not going to be isomorphic to Z4. Finishing this up here gives us 0, 1 here, 1, 0 here. And by symmetry, we get a 0, 1 here. Just double check that. And then a 1, 0 here. But yeah, every element is its own additive inverse. This is not a cyclic group. This is not isomorphic to Z4. How about Z2 external direct product with Z3? I don't want to take the time to make the whole Cayley table, even though it's not super time intensive. Careful, you got to be a little bit more careful with this example. Well, I can write down what it is as a set. Let's take the time to do that. As a set, this is got 6 elements, 2 times 3, right? This would have 6 elements. 0, 0, 1, 0, 0, 1, 1, 1, 0, 2, 1, 2. Those would be the 6 elements. Be a little extra careful when you do your group operations. It's done component-wise, but careful, the operation in Z2 is different than the operation in Z3. So I do 1 plus 1 here, mod 2. You don't have to write the mod 2, but I will for emphasis. Then I do 1 plus 2, mod 3. So I get 0, 0. The additive inverse of 1, 1 then would be 1, 2. Again, getting the identity, I could also write from this something like this. This would be an okay thing to write. The additive inverse, using negative sign in front instead of as a power, of 1, 1 is 1, 2. In general, in the abstract, you're going to want to write your inverse as a power, because in the abstract, we use multiplication. You might wonder, what do we do when the first component is addition and the second component is multiplication? Well, maybe it's probably best to fall back on this notation. Is this cyclic? Well, it is abelian. Both of these groups are abelian. Is this one cyclic? It would be cyclic if I could find a generator. Now I know 1 is a generator of Z2 and 1 is also a generator of Z3 under the appropriate operations. I wonder if 1, 1 maybe might possibly be a generator of this thing, which would imply it would be cyclic. Let's see. Let's calculate multiples of 1, 1, which are analogous to powers in the abstract. This is 1, 1 plus itself. Do the first operation mod 2, do the second operation mod 3. I won't write all the ones, 1s, instead I'll do this. 3 times 1, 1 would be 1, 1 added to itself 3 times. Adding it to itself 2 times gave us this. Now do this operation, the first component mod 2, the second component mod 3. 1, 1's, I already know 1, 1's going to be a generator. How do I know that? Because the cyclic subgroup it generates has to be bigger than 3, because we're not to the identity, 0, 0 yet. 3 divides 6. No other 4 or 5 don't divide 6. Lagrange's theorem I'm also thinking about. 1, 1 is going to have order 6, and it's going to be a generator of this group. By the way, I keep taking the previous answer and putting it on the left over there, and then keep adding 1, 1 to it. We get back to the identity. The order of 1, 1 in this group is 6 in the Z2 external direct product with Z3. Z2 external direct product of Z3 is cyclic. It's isomorphic to Z6. This is true. Let's see this here. Z2, the external direct product of Z2 and Z3 is isomorphic to Z6. It is cyclic. All cyclic groups of order 6 are isomorphic to Z6. Interesting. This one was not cyclic. This one was. That should seem kind of interesting. Sometimes you might get cyclic groups in the external direct product, and sometimes you might not. Could we do something like this and ask the same questions? Okay, even a partial Cayley table would take too long. By partial, when I wrote that, I was thinking maybe doing 2 or 3 products. Let's just do 1 product, okay? Well, first of all, how many elements are in this group? It's 2 times 6. Careful, D3 has 6 elements, right? 2 times 3. 3 rotations, 1 of void, which is the identity, and 3 reflections, symmetries of the equilateral triangle. Z2 is our old friend, 0 and 1. Careful, so you're going to have 2 times 6, 12 elements in this group. Careful, the operation here is addition mod 2, and the operation there is function composition. So when I combine 2 elements from this group, for example, 1R, oops, not that R, 1R120, say, with 1 V, V being the reflection across the vertical. One plus 1 gets done in the first component, mod 2. And in the second component, you get function composition. It's addition there, multiplication, so to speak, there. Really function composition. 0, and then what does R120 compose of B? Let's just find it real quick. Back of the book. R120. Oh, it's got F, F prime, and F double prime. Ah. Okay, maybe I better do it here. Do V first. Then do R120. And that's the same as doing a flip across that diagonal, which I believe we call D, not D prime. It's good to consider more examples on your own. Let me just quickly summarize in 2 minutes some important results. This being the first one. This one's actually not stated as a theorem in the book, but it's maybe worth highlighting. The order of an external direct product of finitely many finite groups is the product of the orders of their factors. The G's being the factors, so to speak, in the product. But again, don't let the plus notation throw you. We still call this a product. The order of an element, this is highlighted as a theorem in the book, in an external direct product of a finite number of finite groups is the least common multiple of the orders of the components of the element. In symbols, we have this. This is going to be a very useful thing for us. Okay. In fact, I will be assigning plenty of problems here from chapter 8 to do on Friday where you will need to use this. Okay. And once you do enough examples, it's pretty intuitive. And we could even think about it in the context of what I erased up here. That 1, 1 was a generator of Z2 external direct product with Z3. The order of this one in Z2 was 2. And the order of this one in Z3 was 3. The least common multiple of 2 and 3 is 6. The order of this element of this external direct product is 6. Going to use that a ton. Okay. Plenty of other theorems in chapter 8 that you should make sure you study and think about and apply to exercises whenever you do. See you on the topic.